Urgent discovery from deep space. 73 light-years from Earth, astronomers have detected something that has eluded science for decades, evidence of a moon orbiting a world beyond our own solar system. Over 6,000 exoplanets have been confirmed since the 1990s. Not a single exomoon has ever been confirmed. Until now, and even now, the discovery comes with a twist nobody expected. In this report, we look at the actual radial velocity data published in Nature, the skeptical reaction already building within the astronomy community, and the strange classification problem this discovery has created, one that has scientists arguing about what to even call the object they just found. Stay with us. To understand why this discovery matters, you need to understand just how badly the search for exomoons has struggled compared to the search for exoplanets. Since the first confirmed exoplanet around a sun-like star in 1995, astronomers have identified more than 6,000 confirmed worlds orbiting other stars, using transit photometry, radial velocity, direct imaging, and gravitational microlensing. Exomoons should, in theory, be common. Our own solar system contains far more moons than planets, but finding a moon orbiting a planet trillions of miles away has proven vastly harder than finding the planet itself, because a moon signal is smaller, fainter, and far easier to mistake for noise or a false positive. Every previous exomoon candidate proposed over the past 2 decades has remained unconfirmed and, in most cases, genuinely controversial. It's worth understanding exactly why moons are so much harder to detect than the planets they orbit. Planets betray their presence in several distinct ways. They can dim their host star slightly as they pass in front of it. A transit. They can pull their star back and forth gravitationally in a detectable wobble. They can glow faintly in infrared light, or they can bend and magnify the light of a background star as they pass in front of it from our point of view. A moon orbiting one of those planets produces the same kinds of signals, but at a dramatically smaller scale, since moons are almost always far smaller than the planets they orbit. Trying to detect that faint secondary signal, layered on top of an already faint planetary signal from a system trillions of miles away, has been compared by researchers in the field to trying to hear a whisper during a thunderstorm. The expectation among many astronomers, once planet hunting instruments improved throughout the 2010s, was that confirmed exomoons would simply follow as a natural next step. That expectation turned out to be wrong, and the search continued coming up empty for years longer than most researchers anticipated. Here's the contrast that makes this new finding so strange. Astronomers weren't even looking for a moon orbiting a planet this time. They found a moon-like object orbiting a brown dwarf, an object that isn't quite a planet and isn't quite a star, sitting in the gap between the two categories. That single detail is why this discovery isn't just a new data point. It's a genuine curveball that the entire field wasn't fully prepared for. Let's get into the actual research. The findings, published in the journal Nature on July 22, 2026, describe evidence for an exosatellite orbiting CD 352722b, a brown dwarf located in a system roughly 73 light-years from Earth. The system itself contains a young star of roughly half the mass of our own Sun, orbited by that brown dwarf, which carries about 37 times the mass of Jupiter, itself too massive to be called a planet, but not massive enough to ever ignite nuclear fusion and become a true star. Our analysis of the team's methodology shows something genuinely novel here. Led by researcher Kevin Hoy, working with 12 colleagues affiliated with Universidad Diego Portales and the European Southern Observatory in Chile, the team applied radial velocity analysis, the same fundamental technique used to discover the very first exoplanet around a sun-like star back in 1995, to the brown dwarf itself rather than to its parent star. Using the Cryers Plus spectrograph mounted on the European Southern Observatory's Very Large Telescope, the team tracked subtle, repeating Doppler shifts in the brown dwarf's light, the tiny wobbles caused by the gravitational tug of something small orbiting it. Between October 2023 and February 2026, the team collected 23 separate observations, spanning nearly 28 months and covering almost 5 complete orbits of the object they were tracking. Their best-fitting model points to a companion with a minimum mass of about 0, 9 times Jupiter's mass, completing 1 orbit around the brown dwarf every 170 days. This particular arrangement creates a genuinely unusual 3-tiered cosmic hierarchy that's worth picturing clearly. At the center sits an ordinary young star, roughly half our Sun's mass. Orbiting that star is the brown dwarf CD 352722b at 37 Jupiter masses, already a strange in-between object, neither planet nor star. And orbiting that brown dwarf is this newly detected companion, at roughly Jupiter's own mass, giving it a mass ratio to its immediate parent body of only about 2. 5% remarkably similar in proportion to how our own moon compares to Earth. It is, functionally, the final link in a 3-object nested system, a structure astronomers had theorized should exist somewhere in the galaxy, but had never actually caught direct evidence of before. Most coverage of this story stops at the headline. But there's a problem, one the researchers themselves are remarkably upfront about, and it changes how you should think about this entire discovery. This object does not meet any agreed, formal scientific definition of an exomoon, because no such formal definition currently exists in astronomy. Within our own solar system, the difference between a planet and a moon is intuitively obvious. A moon orbits a planet, and a planet orbits a star. But this newly found object orbits a brown dwarf, something that is neither a true planet nor a true star. Some researchers in the field argue the object should simply be classified as a planet in its own right, since it sits comfortably within planetary mass ranges. Others insist that classifying it that way ignores the fact that it isn't orbiting a star directly, and that its position around a brown dwarf makes the term planet inappropriate. The paper's own authors settled on a deliberately neutral term for it, an exosatellite, precisely because the field has no better word available yet, and one researcher involved in discussing the find put the underlying tension bluntly, noting that in a system like CD 352722, the boundaries between stars, planets, and moons become genuinely less obvious than most people assume they should be. Here's the twist that makes this genuinely uncertain rather than a clean, confirmed discovery. The radial velocity method, while historically reliable for finding planets around stars, has a track record of producing signals that later needed to be ruled out or revised when applied in unusual or noisy contexts. Independent commentators covering this result have pointed out plainly that a moon's gravitational signature is remarkably easy to imitate through other effects and genuinely hard to confirm through repeated, independent observation. The research team itself describes their own finding using careful, deliberately hedged language, calling it plausible rather than confirmed, and stating explicitly that it remains uncertain whether this exosatellite will ultimately satisfy whatever formal exomoon criteria the field eventually settles on. Let's connect this to the bigger picture, because this discovery sits at the center of a genuine ongoing competition in global observational astronomy. The instrument responsible for this finding, the Very Large Telescope, is operated by the European Southern Observatory, a 16-nation intergovernmental research organization. But the real strategic story here is what comes next. The European Southern Observatory is currently constructing the Extremely Large Telescope, a 39-meter class instrument, the largest optical and infrared telescope ever built once completed, specifically designed to push exactly this kind of radial velocity technique to a level of sensitivity capable of detecting far smaller, more Earth-like exomoons than the roughly Jupiter mass object found here. Europe isn't building this instrument in isolation. The United States has its own competing next-generation ground-based projects in development, the Giant Magellan Telescope and the 30-meter telescope, both racing toward first light within the same general time frame, part of a broader, genuinely global competition among space agencies and international observatory consortiums to be the first to confirm smaller, more habitable zone exomoons, worlds that some astrobiologists argue could ultimately outnumber habitable planets themselves across the galaxy. There's a strategic research dimension here, too. If moons turn out to be common companions of both planets and brown dwarfs across the galaxy, and if some fraction of those moons sit within the habitable zones of their systems, the way several icy moons in our own solar system show strong evidence of subsurface oceans, the entire target list for future biosignature searches expands dramatically. Whichever nation, or whichever international consortium, feels the telescope capable of reliably confirming the first true exomoon will effectively set the technical benchmark the rest of the field measures itself against for the next generation of astronomical research, in much the same way past nations have competed over who reaches a scientific first in space exploration more broadly. It's worth noting how deliberately this particular result was engineered to be a stepping stone rather than an endpoint. The research team themselves state directly in their published paper that although it remains uncertain whether this specific exosatellite will satisfy whatever formal exomoon criteria the field eventually settles on, the achievement marks a meaningful step toward that first uncontroversial detection. Since the same radial velocity technique, once refined further by more powerful instruments like the Extremely Large Telescope, can eventually be applied to progressively smaller and smaller targets. In other words, this discovery functions less like a finish line and more like a proof of concept, demonstrating that hunting for moons around brown dwarfs, rather than only around planets, is a genuinely viable strategy going forward, one that instantly widens the pool of targets every competing observatory program now has reason to prioritize. Let's recap what we know. Astronomers using the European Southern Observatory's Very Large Telescope have detected a repeating Doppler signal consistent with a roughly Jupiter mass object orbiting the brown dwarf CD 352722b, a companion completing one orbit every 170 days based on 28 months of careful observation. The finding is described by its own discoverers as plausible, not confirmed, and it has ignited a genuine classification debate over whether this object even qualifies as an exomoon at all, given that no formal definition of the term currently exists. If the very first plausible exomoon in scientific history turns out to be something science doesn't even have an agreed name for yet, what does that tell us about how much we still don't understand about the worlds and the moons scattered across our own galaxy? And how many more strange, unclassifiable objects are still waiting out there for the next generation of telescopes to find? We want to hear your theories in the comments below. Stay informed.